The second talk in this session will be given by Nick on handling higher order effectful operations with judgmental monadic laws.
Thanks very much. So this talk will be about, indeed, handling higher order effectful operations, and a little bit less about with judgmental monadic laws. Let's see where we get. So the story I want to tell starts with something that we should all know, which is we have programming languages, and they involve a relationship between software engineers and language designers, right? So your software engineers want to write some code, and that code gets executed or compiled by the compiler, and maybe you want the compiler to produce efficient code, or maybe code with like debug instructions or something like this in it, and the compiler takes care of all sorts of things like effects. But there are problems with this. So new effects can't really be added unless the compiler sort of supported them in the first place in some way. Existing effects can't be modified by the software engineer because they don't have access to the compiler. Maintenance is difficult. If the software engineers find a bug or something, they have to wait for the compiler writers to fix it. And compilation targets are fixed, so you can only have the two modes that were enabled by the compiler to start with. So we tried to fix this problem by adding effect handlers to the languages that we work with. So here's the same story, except we add one feature, that's support for handlers. And what that allows is for software engineers to modify various effects in their own right. And they can also add a whole bunch of effects that weren't conceived of in the first place. And it actually means that there are fewer features needed in the compiler as well. And finally, because they can define their own sort of semantics for code, they can produce new sort of output semantics. So for instance, they can decide to do some analysis on how much time it takes for functions to execute, for example, or whatever they might want. Okay, so that's kind of the motivation for what we're doing. And I'm not going to go through every single example here, but the point is that programming languages provide lots of different operations, and there are lots of different effects that might be executed. And so the real question is, can programmers add effects and control their implementations? And we think that effect handlers are a good way of doing that. They provide an interface for defining operations that are modular and composable. So I'm going to go through a kind of very concrete example of what this means. So suppose I just have a simple hello world type example here. It prints off, enter your name, then you type in your name and it says hello to you. Fine. So I can execute this. I type in my name, it says hello Nick, everything is fine. And suppose now I really wanted to encrypt anything that's been printed. So I can type this, and I just put an encryption under every single print that I have. And so eventually I can say hello encrypt. It's all been encrypted, it's backwards. And then I type in my name the normal way, and then of course it encrypts everything on the output. All right, fine. So now suppose I want to encrypt things, but I also want to time how long it takes for the user to input some data. So we have the standard print here, then we have a get time before and after we do the get line, and then we're going to type out the print but not encrypted, and then we'll encrypt the whole thing. Okay, so then we can execute this, and then it says, what is your name encrypted? I type it in, it gives me the time not encrypted, and then I can carry on with the encrypted output. Fine. So how could we maintain these different versions of this code for different purposes, right? So suppose that there were other things you had in mind. Maybe you wanted to do you want to do some debugging on this. Maybe you want to do it in production mode, or with more testing information, or with timing metrics, et cetera, et cetera. What would we do, right? If we're teaching this to first-year undergraduates in sort of good software engineering practices, they would say something like, well, maybe I just modify the code. Well, no, you shouldn't modify the working code. That's not a good way to work, right? You should keep the code that works as is, right? But maybe what you want to do then is you want to have copies of the code like we've got here with different versions, and you call out to the one that you want. But the tricky thing now is if there's a bug in the original piece of code, then you've got n different versions to maintain, and that's not good either. So maintenance is also a problem, so you don't want to do that. And so the thing that we turn to is algebraic effects. We say, okay, maybe what we can do instead is reinterpret the way the operations work themselves. That way we can keep the original code as is, and we can yet change the meaning of that code when it's executed. So here's that same code on the left-hand side, and on the right-hand side, I'm going to just show you what you can do with effects. So it's the same piece of code. We still have the hello. The only thing that's changed is the type signature, where I'm actually saying this code involves printing and getting. And what I can have instead is this thing called a handler. And this handler says it's going to intercept any prints and produce prints. So here it is intercepting any print message, and it's going to add an encryption to it instead. And here's a different handler, which intercepts any get lines and replaces those with stuff that involves time, does get line, and also prints. So when it sees a get line in your code, it's going to say, I'm going to get the time, then I'm going to do the actual get line, then I'm going to get the time, and print out the time that it took to do something. And what this allows now is for us to be able to compose handlers together to give a new semantics to the kinds of things that we're doing. So for example, here's the encrypted time handler, which first encrypts the words that we have, then does the timing stuff, and then produces some I/O action. So if we were to execute that, we would get the version where the printed stuff has been encrypted, but the time hasn't been encrypted because that's not gone through the encryption handler at this point. But of course, and the good thing here is that we've managed to modify our behavior of the hello program without modifying the hello program itself, right? We've changed the way that the operations have been interpreted, and we're happy because we've gone beyond the first year where we've had to change our code in bad ways. But what we can also do now is we can we might be able to commute our handlers down here. And by changing the order of these handlers, what we're saying is we're going to get some timing information, and then that's going to output some strings, and all of that's going to be encrypted, along with everything else that's been printed too. So if we do the timed encrypted handler on the same hello program, then you get the encrypted prompts, you get the unencrypted get line because that's when you're typing things manually. And then, of course, the time has been encrypted now, as well as the final messages. So what's nice about this is that we've been able to easily add additional behaviors simply by changing the handlers that are dealing with things. So far, so good. This is the standard effects and handlers story. But now there's something that is a little bit perplexing. So suppose we have a program that looks like this. It's a program that does some stuff, and then at some point says, handle the hello program with a timed encrypt. I suppose we've got a different program that does basically the same, but uses the different handler instead. So this time it's doing encrypted timed. The question becomes, what if I wanted to choose between these two different programs, and I want to be able to do that by modifying the way that we're going to handle things, right? And this is almost the same question that we had just a minute ago, except that I'm now asking myself, how do I change what handlers are being chosen, rather than how do I change what the operations are doing? And we want to do this in a way that's suitable. So we've gone through the reasons why this is bad for ordinary operations. It's also going to be bad for handlers. So we can't just modify the handlers and say, well, I've changed my mind and delete all the code and replace it with something else. And so again, we want to say, well, can we perhaps somehow reinterpret the handlers themselves in different contexts? So can we have handlers? That would be nice. So perhaps along the way we decide what we're going to do instead is have a sort of censor operation. So here we have some kind of censoring with an encryption scheme, and then we might have two handlers that deal with that censoring and does it in an uncensored or a censored version. But the trouble is that censor itself is not a first order thing. It takes as one of its parameters this hello program, and which we can sort of see here as this parameter here. And unfortunately, that just means it's not an algebraic operation. It doesn't fit what the framework is expecting. It's what we call a high-order effect, and that's the kind of thing that we deal with in our framework. So that's kind of the motivation for this, and I'm going to go into the more sort of theoretical construction around how we get there. So we're using a kind of CBPV type semantics where we've got pure values. So here the turnstile has no sigma annotation. That means it's a pure value. And so we can construct things like values, we can construct things like operations, and we can sequence things using let bindings in this way. And typically what we do in this domain is we talk about algebraic operations, which are just a shorthand for saying that we have a let binding followed by some kind of computation. Okay, and there are lots of operations that we can handle in this way. Again, I won't go through those in too much detail, but the point is that you have some kind of fixed parameter and some kind of arity, and you can pass all these through, and it all just works as you'd expect. So the key point with effect handlers is that what we want is the handlers to sort of reinstall themselves automatically into the continuation. At least that's the perspective for deep handlers. So we can see that in the rule for how we do operations. So with a particular operation, what we're going to do when we handle with some h, big H, is we execute the kind of interpretation of that operation, which is sensitive to the parameter v and k that's going on here, so sensitive to the parameter and the continuation. And what we're going to do is just substitute the actual parameters into the formal ones. But in particular, in the continuation parameter, we reinstall the handler big H on the residual program Q that we're going to carry on with, right? And this is quite key. It's what we would call a deep handler because it's automatically taking care of the bureaucracy of reinstalling handlers for you. And I think that's really critical because it means that when you're writing algebras for these things, or when you're writing the semantics for these things in these little h's, you don't have to think about what's going to happen with the recursive call. The framework is taking care of that for you. That's really critical here. And then, of course, this framework allows you to give different versions of handlers. And so here's the kind of more theoretical way of saying exactly the same thing that I said earlier on. We have different handlers. That's great. But if we want to have catch, we can sort of imagine it being a handler like this. But in a program that has multiple nested catches like this one, we might ask ourselves the question of, well, how about if I want to reinterpret catch as retry or some other semantics instead, which is the problem that I was showing you in the concrete earlier. And we know we don't want to modify the program P so that we replace catches with retries. We know we don't want to redefine catch as retry. That would be just modifying the source code of that. What we need instead is the idea of making catch an operation and then handle that somehow. So one way of doing that, and I think it's the one that most experts ask me first, like, why don't you just do this, is what I call the quick and dirty approach, right? What you do is you have the catch operation, and as its parameter, you put in code. You say, well, there's nothing wrong with code being a parameter. We can just pretend it's just a ground type like everything else. Maybe it complicates the denotational semantics somewhat, but somebody clever can sort that out for us. That's fine. But that's what people do in practice, and so you can imagine you've got your program P, your program H, and we're going to handle these. And the way that we might deal with this is we could create this new handler called retry, which observes the catch operation, which now has programs as its parameter, and does something like this. Now, I don't really care too much about what this is actually doing. What I want to point out is that in the handling clause A, big H here, we are reinstalling various handlers into the subcomputations. So under catch, we have our program and our handler. We need to execute P and handle it with this big H, and we also need to execute H and handle that with big H. And the point I want to make here is that this really undermines the fact that we're using deep handlers in the first place. Because now for these kinds of operations, where the payload, the parameters contain programs themselves, you, the handler writer, have to think about reinstalling things yourself. And I think just 2 minutes ago I said, isn't it a good thing that in deep handlers we don't have to do that? Well, here we're doing it all over again. So the big point is that we want to avoid this explicit reinstallation, and we want that to be taken care of by the machinery itself. And that's where we get onto doing scoped operations in a slightly different way. So we can basically redesign our language so that we have native support for these things called scoped operations. And they essentially look very similar to before. They still have this idea of parameter and arity, but they're going to be examples where we have, as one of our parameters, or as the continuation, is going to tell us how many programs are going to be needed to spawn off to deal with whatever interesting effects that we might have. So for example, catch, so there's one operation catch that takes in one parameter, and it has arity 2, which means it has 2 programs that you might be interested in once you're dealing with this operation. So the first one being the ordinary program, and the second one being the program that handles the effects of that one. Or here's another one with the same signature, which is parallel operation. So there's one parallel operation, and it wants to do P1 and P2 in parallel, and so it takes in these 2 arguments. With is another example. So with says, with some resource R, that R might be something like a file or a network socket or something like that. We want to have one program that comes out, and that program is going to be somehow sensitive to that resource that's in play. Another example is maybe like some control structures, like if or while loops. So an if takes in some Boolean, and then it produces 2 programs, or at least 2 programs might be sensitive to that Boolean. So this might be if you want to, I don't know, have a lazy version of if then else, or maybe an eager version that executes both branches, or who knows what. Maybe you're doing some kind of like static analysis of your code. You want to reinterpret how if works, and similarly with while. So the only real difference so far between these and scoped operations syntactically is that we're just indicating that they're scoped with these curly braces rather than the round braces. That's all that's going on. And so at this point, I think it's good to just reflect a little bit about on the different sort of presentations of operations that we've got. So we have the generic operation that we started with, and what I sort of briefly noted was that we have a kind of rewrite rule that just says, actually, generic operations are just the same as algebraic operations, which have this round parentheses around to say where the continuation is. And that's subject to this law that says that you can always sort of you can commute the let into the parameter. One way of reading this particular law is to say that this parameter is kind of irrelevant, right? It's that you can always just bind freely. And so in a sense, that's why generic operations don't need this in the first place. So long as you have let bindings, you're fine. But the reason that it's often stated this way is because we enjoy writing the handler operating semantics with that continuation K explicitly marked so that your particular algebras can deal with that continuation result and do something with it. So in a sense, the reason that this is useful is for the description of handlers, although in terms of syntax, this might be a more sensible way of doing it. The scoped operation is different, right? The scoped operation has this parameter here, which denotes the sort of continuation of programs that you want to handle before you continue after this operation. And I think some of you will validly say, hang on a minute, you're just playing tricks here. This is exactly the same as the algebraic operation. All you've done is changed the brackets, right? That's not a sensible distinction to be making. My point is that actually this is not a law, right? We don't have the algebraicity condition, which means it's relevant whether or not we have the operation by itself or whether we have it under a let binding. Those are two distinct things, and they shouldn't be confused. So that means that when we try to handle such scoped operations, so here's the scoped operation, we need to be a bit more careful with what we're doing. And ultimately, you can see that we have this handler H, which deals with the continuation explicitly here. There's something to do with polymorphism going on here, which deals with the fact that you could have nested scopes, and you don't quite know how nested you are. You need to deal with those differently. But the point that's important is that when you're faced with something like this construct here, where you have let A equals op vj in Q, you really can't translate that into just a simple scoped operation as you did with the algebraic version. You can't just do away with the lets and absorb that into the continuation parameter. What you need to do instead is explicitly handle the operation with the J jump parameter, let's say, and interpret Q separately, and then somehow combine these two in some sensible way, preferably doing this thing first before this thing on the right. Okay, so we need to combine these two computations, and if you look at their types, you can see this has type MA, and this type has type MB given some A. Well, that reminds us of something if we're familiar at all with monads. But that's not where the literature went. So the literature went slightly different. Bosman, Vandenberg, Tang, and Shrivers wrote a paper about this problem where they do the same thing that you would do in the algebraic effects setting. That is to say, you extend your scoped operation with an additional continuation, just like you did with the generic operations for algebraic. And then you give a semantics where the handling algebra H takes into account the continuation that comes off of that and continues from that way, right? And so in this way, the thing to note is that your algebra is sensitive then to the continuation on the outside of this. And so we have kind of like you can imagine this being called like the algebraic scoped version or something like this, I don't know, right? But there was a different solution, which is the one that we take in this paper. And the solution is to say, actually, maybe we should be handling let. We keep operations just as they were, we keep val just as it was, but we now explicitly have a way of dealing with let. So that means that we're going to have handlers that need to take into account this M parameter, which basically has to handle the context for a let. So it has some P, which is a program, Q, which is a continuation of this, and then brings you back to this point. Now, if you look at this, you get really suspicious because now you really are looking at bind. If we just compare the two, I just want to sort of emphasize that both of them achieve roughly the same thing, right? But the difference between them is a bit like the difference of the universal property of lists. There are two universal properties of lists. There's lists as the initial fixed point of the particular functor where you've got a value constant onto some stuff. And you've also got the universal property of lists as a monoid where you keep hold of that monoid structure. And we're seeing these two different versions here where in this second one, we're kind of remembering the fact that we're interpreting into a monad. And so we're allowed to kind of use bind in our semantic domain. What that means is that when we write equations in the style of number 2, we're allowed to talk about bind. We're allowed to talk about what happens with the monad itself, which means we can talk about interactions with bind and other operations, which we couldn't do in the first version. So the deep scoped handler looks something like this, where essentially we're going to say we want to be able to take care of the let op version of things. And the idea is basically that we reinstall the handler under each of the jump parameters here, where we reinterpret all of those. And then once we've finished interpreting all of the jumps, we then bind onto the interpretation of Q prime. But this bind here, so this is sort of syntactic sugar for the M that comes out of interpreting this thing. So you can just imagine that this operation, which is sensitive to P and Q and X, can be turned into a bind operation. And if you know that you're interpreting into a monad, that really is the bind that you want to play with. So I think that's basically the main message of the paper. It's that when we're handling scoped things, we have a choice, and it's sensible to work in the understanding that you're going to be interpreting things into a monad. That allows you to have a richer language for equations afterwards where you can incorporate that in your understanding of what's going on. So the paper itself takes a very different exposition to what I've given you here, right? So in the paper, we do the presentation of the theory not with the traditional gamma and turnstile presentation, but rather we go quite categorical, and we work with a logical framework instead. And our computational semantics are proven using realizability models instead, which prove consistency of the model and give us the executional semantics of that as well, so that we can actually have assemblies that tell you that you can execute our programs. So that's how we deal with sort of the operational side of things. And then rather than working with traditional logical relations, we work with syntactic take computability and then do our proofs that way. So I see that I've got about 3 minutes left to talk. So I was going to call this the end of talk, but maybe it's not really the end of the talk. To give you just kind of a quick flash through some of the constructions of doing system F omega in a logical framework, we'd get something that looks like this. So the logical framework is basically a Martinov type theory, which contains judgments J and various widgets that you would expect. And I just wanted to sort of have a side-by-side comparison for you for what things look like in the paper. So on the left-hand side is the traditional gamma and turnstile presentation that you'd be used to, and on the right-hand side is the exact translation that we'd have in the paper. So here's the rules for kinding. Here are the rules for kinding, application, and abstraction on the left-hand side, which are all usurped by this single rule on the right-hand side. It's just witnessing an isomorphism. And this is the kind of compact stuff that we really enjoy in that paper. Of course, that's achieved by just expanding some definitions, but that's kind of the purpose of this. And again, on the right-hand side, we're doing some interesting logical framework stuff. And the kind of key contribution of the paper itself is actually not just this, it's actually working towards system F omega ha, which is F omega extended handlers. This is basically where we add in a CBPV style, thunks, where we've got forcing and thunking. We can talk about things like the laws of computations as you'd expect. And then the handle construct that I gave you earlier on is slightly generalized so that we're dealing with higher order signatures instead. So the rule that we give in the paper is this, but that translates to something like this in the turnstile way. And what's interesting is that the proof basically is about whether or not we can have well-behaved enough programs such that this works out. So as I said, this paper is supposed to be not just an investigation of, let's say, higher order operations and how we can handle them. I think that the message of the paper is that we should be really thinking about bind itself when we're giving semantics to things which involve sequential computation. That's not news, but it seems to be news when we're thinking about algebraic operations. The second thing is it's really a tutorial in, well, maybe tutorial is too strong a word. It's an example of how you might do semantics in a way that doesn't involve the traditional gamma and turnstile. Thanks very much.
All right, thank you. So I think we have time for maybe one quick question.
I'm just a quick question about the dynamics. You know, how you started designing this work? Were you more on the turnstile side or more on the categorical? You know, like
this was designed more from the categorical framework
so
perspective.
since the beginning, and
Yeah.
you know, and what it brought you, you know, and you know why it was in the end a natural option.
Yeah, that's right.
I think it's a good question.
Yeah, it's a broad question. So I think the goal was really what happens when you kind of stubbornly stay down the categorical route right the way down, and then you come up with some nice semantics, and then the rest is
Kind of guideline. I mean, it was a guide.
yes,
towards,
exactly. It was the
like,
guiding principle.
as it should. Yeah. Okay. Thanks.
Yeah.
Right, so thanks, Nick, again.
Thanks.